The focus of this video clip will be to go over how to do some of the calculations for the clock reaction lab, specifically part number 2, the calculations for that point of our lab exercise. Using the part 2 data, we're going to end up making 2 separate graphs. One of the graphs, which is number 18 in the lab questions, is going to have the temperature of the trial on the vertical axis and then the average time that it took the reaction to run to completion along the horizontal axis of the graph. Purpose of this graph is just to look at what's the relationship between when we change the temperature, what impact does it have on the average time, or which the average time tells us the rate of the reaction. A longer amount of time would indicate the reaction is going rather slowly. A short time would indicate, or a lesser amount of time would indicate that the reaction proceeded at a fairly high rate. Let's next take a look at question number 20. To do number 20, we have to use the rate law that we developed from part number 1 in the lab exercise. Once again, our rate law would be the expression rate is K times the concentration of our chemical KiO3, which was our chemical A in the lab exercise, raised to some exponent, which is the order of reaction. When calculating this for part 2, we're going to use for rate the average rate for a given temperature trial. Inside our brackets here represents the concentration of chemical A in each one of the trials. Now in part 2 in the lab, keep in mind the concentration of chemical A was kept constant from one trial to the other as we were looking at the influence of temperature on the rate of the reaction. So chemical A was kept constant throughout the lab exercise. The M, or our exponent here, represents the average order of the reaction with respect to chemical A. The average order we determined in part 1 of the lab exercise. So whatever you got with your lab colleague as the average order for a reaction with respect to chemical A, that'll be used for each one of the calculations here in part 2 of the lab exercise. So for example, what we'll do is for each different temperature trial, insert the average rate of reaction here for the rate. The concentration of A is 0.005, and then utilize whatever your average order was determined in part 1 of the lab. So if your average order was, say, 3.2, we'd use that for each one of our calculations now in number 20. What we'll solve for then is our what's called our rate constant K. Now the rate constant K is something that remains constant for a given temperature. The only thing that can change our value of K is to alter the temperature conditions of the reaction. So once again, our rate constant, which is a lowercase k, that remains constant for a given temperature. The only thing that can change our value of K would be to change the temperature conditions under which we run the reaction. Now we have our rate constant K in our rate law expression, which is utilized to help us find the rate of a given reaction. In the lab exercise, we're to determine what the value of K is for each one of the different temperatures at which we ran the particular reaction. So find K for each different temperature trial that was done in the lab exercise. Let's now take a look at question number 22. For number 22, we're going to use an equation which is known as the Arrhenius equation. Now this is one particular form of the Arrhenius equation in which we take the natural logarithm of our rate constant K. It's equal to negative energy of activation divided by our R value, the gas constant, R, and then 1 over our absolute temperature. Now let's take a moment and compare this equation, one of our fan favorite equations, the old y equals mx plus b, our equation for a linear relationship. Now comparing these two, we can see our y value would be natural logarithm of our rate constant K, our x value 1 over the absolute temperature, and then our slope here would be the negative of the activation energy divided by R. Now, based on this comparison of the Arrhenius equation with y equals mx plus b, it gives us some information we use to plot a graph, which will provide us with some useful information. For example, let's make our y-axis be represented by the natural logarithm of our rate constant k at all the different temperatures in the trials we ran in the lab exercise. Likewise, let's make our x-axis on our graph specifically be 1 over our absolute temperature. Now, by making our plot where our y-axis is the natural logarithm of our rate constant k and our x-axis is 1 over temperature, this middle part, negative EA over R, the slope of our line would be equal to negative energy of activation divided by R. By making this plot with our y-axis natural logarithm of our rate constant k and our x-axis 1 over t, we'll produce a linear relationship. Our slope in the plot, the slope would then be equal to the negative of the energy of activation divided by R. Rearranging this, we can readily find our energy of activation. Rearranging, we now have that negative R times the slope of our plot in this line, negative R times our slope, will provide us with the energy of activation for our reaction. So again, by making our plot where we have our natural log of k on our vertical axis, or our y-axis, and making our x-axis 1 over our absolute temperature, when we plot this, our slope of the line would be negative energy of activation over R. Rearranged allows us to get negative R times our slope to provide us with a way to calculate from our graph our energy of activation for this particular reaction. By determining our energy of activation, it's a means of getting what's the size of the minimum amount of energy, our energy of activation, for the particles to collide in order to get our reaction to be successful.